September 8, 1944, 6:43 p.m., Chiswick, West London. Mrs. Ada Harrison was preparing dinner when the world exploded. No warning siren, no engine sound. Just a sudden, catastrophic detonation that obliterated 3 houses and killed 3 people instantly. Minutes later, another explosion struck Epping 17 miles away. Again, no warning. No aircraft overhead, just death falling from the stratosphere at 3 times the speed of sound. The V-2 rocket had arrived, Hitler's vengeance weapon, the world's first ballistic missile, a technological marvel that represented the pinnacle of German engineering and the desperation of a dying regime. But here's what the Nazi propaganda never mentioned. The V-2 program killed more people building it than it ever killed as a weapon. It consumed resources that could have produced 24,000 fighter aircraft. It represented billions of Reichsmarks spent on a weapon that changed absolutely nothing about the war's outcome. The V-2 wasn't alone. Nazi Germany poured astronomical resources into dozens of wonder weapons that promised to turn the tide of war. Jet fighters that arrived too late, super heavy tanks that couldn't cross bridges, acoustic torpedoes that didn't work, rockets that exploded on launch pads. This is the story of how desperation, ideology, and megalomaniacal ambition created weapons that failed spectacularly. How Nazi Germany's wonder weapons program became a cautionary tale of technology without strategy, innovation without resources, and brilliance without wisdom. The V-2, engineering marvel, strategic disaster. The story of the V-2 rocket begins not with Hitler, but with a young German engineer named Wernher von Braun, who dreamed of reaching the stars. In 1932, von Braun was conducting rocket experiments on a farm outside Berlin when representatives from the German army approached him. Captain Walter Dornberger, head of the Army's ballistic section, had been watching the young engineer's work. Germany was forbidden from developing long-range artillery under the Treaty of Versailles. But rockets? The treaty said nothing about rockets. Von Braun accepted military funding, and his dream of space exploration became entangled with weapons development. By 1936, the team had moved to Peenemünde, a remote testing facility on the Baltic coast. It would become the birthplace of modern rocketry and one of history's most controversial weapons programs. The technical challenges were extraordinary. No one had ever built a rocket that could travel 200 miles. The vehicle would need to reach altitudes of 50 miles, survive temperatures exceeding 1,000 degrees, and deliver a 1-ton warhead with any semblance of accuracy. Early attempts were disasters. The A-1 rocket exploded on the test stand. The A-2 managed a few successful launches, but couldn't be weaponized. The A-3 failed 4 consecutive launch attempts in 1937. Each failure consumed resources and time that Germany couldn't spare. But von Braun's team persisted. The breakthrough came with the A-4, later renamed the Vergeltungswaffe II, or Vengeance Weapon 2. On October 3, 1942, the first successful V-2 test sent a rocket 118 miles downrange and 53 miles high. It was humanity's first object to reach space. Dornberger reportedly proclaimed, "Today, the spaceship was born." Von Braun's response was more ominous. The rocket worked perfectly, except for landing on the wrong planet. Hitler, initially skeptical of rockets, became obsessed after viewing footage of the successful test. He envisioned thousands of V-2s raining down on London, breaking British morale and forcing a negotiated peace. In December 1942, he authorized full-scale production. The reality of mass-producing rockets proved nightmarish. Each V-2 was essentially a handcrafted object requiring 13,000 individual parts. The gyroscope alone needed components machined to tolerances of 1,000th of a millimeter. The fuel system used liquid oxygen and ethanol, both difficult to produce and store. The guidance system relied on analog computers that were primitive even by 1940s standards. Labor was another problem. Building V-2s required skilled technicians, but Germany's manpower was depleted by years of war. The solution was slavery on an industrial scale. In August 1943, British bombers destroyed much of Peenemünde. Hitler ordered production moved underground to Mittelwerk, a facility carved into the Kohnstein mountain near Nordhausen. The complex consisted of 30 miles of tunnels where concentration camp prisoners would build rockets under conditions that defied human comprehension. Prisoners from Mittelbau-Dora concentration camp worked 12-hour shifts in tunnels with no ventilation, no sanitation, and barely any light. They slept in the tunnels, breathed toxic fumes, and died by the thousands. Disease was rampant. Malnutrition was universal. Guards beat prisoners to death for minor infractions or no reason at all. Arthur Rudolph, production director at Mittelwerk, implemented a system where prisoners who couldn't meet quotas were hanged in front of other workers as motivation. Jens Christian Wagner, a historian who studied Mittelbau-Dora, documented that approximately 20,000 prisoners died building V-2 rockets, more than twice the number killed by the weapons themselves. The rockets themselves remained deeply flawed. Of approximately 6,000 V-2s produced, nearly 2,000 exploded on launch pads or shortly after liftoff. Quality control was impossible when workers were literally dying at their workstations. Prisoners engaged in subtle sabotage when possible, misaligning components by fractions of millimeters that would cause failures miles downrange. The first operational V-2 attack came on September 8, 1944. Over the following months, approximately 1,400 V-2s struck England, primarily London. Another 1,600 targeted Antwerp after its capture by Allied forces. The weapons killed approximately 9,000 people, most of them civilians. But what did this accomplish strategically? Nothing. British war production continued uninterrupted. Morale remained intact. The weapons were too inaccurate to hit military targets and too few to seriously damage cities. A V-2 could land anywhere within a 10-mile radius of its target, making it useless for precision strikes. The economic cost was staggering. Each V-2 cost approximately 100,000 Reichsmarks, equivalent to 2 Tiger tanks. The total program consumed an estimated 2 billion Reichsmarks, roughly $8 billion in today's currency. This could have produced 24,000 Messerschmitt Bf 109 fighters, which might have actually affected the war's outcome by challenging Allied air superiority. Albert Speer, Hitler's Minister of Armaments, later wrote in his memoirs, "The V-2 program was a mistake. The funds and materials used could have produced a significant number of fighter aircraft. This would have been far more valuable than a weapon that produced minimal strategic results." The V-2's greatest impact was psychological, and even that was limited. Initially, Londoners were terrified by weapons that struck without warning, but humans adapt. By late 1944, V-2 attacks became another wartime hazard to endure, no more or less frightening than conventional bombing. The accuracy problem was fundamental and unsolvable with 1940s technology. The guidance system relied on gyroscopes and analog computers that couldn't account for wind, atmospheric variation, or manufacturing tolerances. Even under ideal conditions, hitting a city-sized target at 200 miles was considered success. Von Braun's team experimented with radio guidance, but Allied jamming made it unreliable. They tested beam riding systems where rockets followed radio beams, but these were equally vulnerable to countermeasures. The fundamental problem was that ballistic missiles in 1944 were like throwing rocks at a target 200 miles away while blindfolded. The V-2 program also suffered from competing priorities and Nazi bureaucracy. Heinrich Himmler's SS fought for control with the army. Göring's Luftwaffe demanded resources for its own programs. Hitler constantly changed priorities, demanding impossible production increases while simultaneously ordering design modifications that delayed production. In March 1945, with Berlin surrounded and the Reich collapsing, V-2s were still being launched. The last operational rocket struck London on March 27th and Antwerp on March 28th. By then, Allied armies were crossing the Rhine, and Soviet forces were fighting in Berlin's suburbs. The wonder weapon had accomplished nothing except consuming resources and killing thousands of slave laborers. After the war, both the United States and Soviet Union scrambled to capture V-2 technology and personnel. Von Braun and 500 German engineers surrendered to Americans, bringing with them plans, components, and expertise that would eventually send humans to the moon. The Soviets captured Mittelwerk and shipped entire production facilities to Russia. The V-2 became the ancestor of every ballistic missile, military and civilian. ICBMs, space launch vehicles, even the Saturn V that landed on the moon descended directly from von Braun's wartime rocket. The technology was revolutionary. But as a weapon deployed in World War II, it was an expensive, ineffective failure that killed more of its builders than its targets. The Me-262, the jet that came too late. On July 18, 1942, test pilot Fritz Wendel pushed the throttles forward on a revolutionary aircraft at Leipheim Airfield. The Messerschmitt Me-262 accelerated down the runway, turbojets screaming. At 373 mph, it lifted off, becoming the world's first operational jet fighter to fly on jet power alone. Wendel later reported, "It was as if angels were pushing. The Me-262 could reach 540 mph, 100 mph faster than any Allied fighter. It could climb to 30,000 feet in 7 minutes. Its 430mm cannons could destroy a bomber with a single burst. In the hands of a competent pilot, it was virtually untouchable. It should have changed the war. Instead, it became a case study in how poor decisions, competing egos, and impossible strategic situations can negate even the most advanced technology." The Me-262's development began in 1938 when Messerschmitt received a contract for a jet-powered fighter. The concept was sound, but the execution faced enormous challenges. Jet engines barely existed as functional prototypes. Materials that could withstand the heat and stress didn't exist. Control systems for aircraft flying at unprecedented speeds hadn't been developed. The first prototypes flew in 1941 using a conventional piston engine in the nose because the jet engines weren't ready. When Junkers finally delivered the Jumo 004 turbojet in 1942, it produced 1,280 pounds of thrust but had a service life of just 25 hours before requiring complete replacement. Think about that. The engine lasted 25 hours. A typical Allied fighter engine lasted 500 to 1,000 hours between overhauls. The Jumo 004 had to be treated as a disposable component, manufactured cheaply and quickly, then thrown away after barely breaking in. The material shortage was crippling. Jet turbine blades needed heat-resistant alloys containing nickel and chromium. Germany had limited access to these materials due to Allied blockades. Engineers resorted to using mild steel with aluminum coating. The result was engines that frequently disintegrated mid-flight, shredding turbine blades that would puncture fuel tanks or damage control systems. Despite these issues, the Me-262 program progressed. By 1943, test pilots were regularly flying prototypes. General Adolf Galland, commander of the Luftwaffe fighter arm and one of Germany's top aces, flew in Me-262 in May 1943. His report was enthusiastic. "It is as if an angel is pushing me. This aircraft opens up completely new tactical possibilities." Galland immediately recognized that the Me-262 could challenge Allied bombing campaigns. Its speed made interception of B-17 formations possible, even when they had fighter escort. Its heavy armament could destroy bombers quickly. He recommended immediate mass production. On November 2, 1943, Hitler visited Messerschmitt's facility and asked Chief Test Pilot Willy Messerschmitt a question. "Can this aircraft carry bombs?" Messerschmitt, wanting to please Hitler, said yes. Technically, the Me-262 could carry 1,000 pounds of bombs. Practically doing so negated its speed and maneuverability advantages. Hitler immediately declared the Me-262 would be Germany's new fast bomber, capable of striking Allied invasion forces. Galland and other Luftwaffe commanders were horrified. Converting a revolutionary interceptor into a mediocre bomber made no tactical sense. But Hitler was obsessed with offensive weapons. Fighters were defensive. Bombers could strike back. The Führer's word was law. For months, the Me-262 program was suspended while engineers redesigned the aircraft to carry bombs. Bomb racks were added, bombing sites were installed. Training programs focused on ground attack rather than air combat. Galland later estimated this delay cost Germany 6 crucial months of Me-262 production during late 1943 and early 1944 when the Luftwaffe was being systematically destroyed. The bomber variant, designated Me-262A 2A Sturmvogel, Stormbird, proved as ineffective as predicted. Flying at 540 mph made accurate bombing impossible with 1940s technology. The pilot couldn't see the target until past it. The aircraft was too fast for the bomb sight to calculate properly. Most bombs missed by hundreds of yards. Meanwhile, Allied bombing intensified. By early 1944, Germany was losing 400 to 600 fighters monthly in combat, with pilots killed faster than replacements could be trained. Production facilities were being systematically destroyed. Fuel was becoming scarce, experienced pilots were dying, the Luftwaffe was collapsing, and the weapon that might have helped was being converted into a bomber that nobody wanted. Finally, in November 1944, Hitler grudgingly authorized fighter production of the Me-262, but by then, it was far too late. Production faced insurmountable challenges. Building jet engines required precision manufacturing that was difficult under peacetime conditions and nearly impossible with factories being bombed regularly. Skilled workers were dead, wounded, or conscripted into infantry units. Materials were scarce. Allied bombing specifically targeted ball-bearing factories, which crippled production of the high-precision components jets required. The Me-262 also required specially prepared runways. Its takeoff speed was 109 mph, much higher than conventional fighters. It needed longer runways than most German airfields possessed. Once airborne, it was deadly. But getting airborne made it vulnerable. Allied fighter pilots quickly learned that Me-262s were most vulnerable during takeoff and landing. P-51 Mustangs and P-47 Thunderbolts began patrolling known Me-262 bases, attacking jets when they were slow and helpless. Many Me-262s were destroyed before ever engaging enemy aircraft. The operational units that did form achieved remarkable kill ratios. Jagdverband 44, commanded by Adolf Galland himself after he was removed from his command position for criticizing Hitler's bomber decision, claimed 50 Allied aircraft destroyed for just 27 Me-262s lost in combat. Major Walter Nowotny's unit achieved similar success before Nowotny himself was killed, possibly by a technical failure rather than enemy action. But these successes were tactical, not strategic. By late 1944, Germany faced overwhelming Allied superiority. The Luftwaffe might destroy 50 bombers in a day, but 800 would get through. Losses that were catastrophic to Germany were acceptable to Allies who could replace them within days. Fuel shortage became critical. The Me-262 consumed fuel at 3 times the rate of conventional fighters. With German oil facilities being systematically destroyed and synthetic fuel production collapsing, many completed Me-262s sat on airfields without fuel to fly. Pilots trained on the jets watched helplessly as Allied bombers passed overhead, unable to take off because the fuel that should have powered their revolutionary aircraft didn't exist. The training problem was equally insurmountable. Jet aircraft flew differently than propeller-driven fighters. The engines responded slowly to throttle changes. The high speed changed all combat geometry. Pilots needed extensive training to operate them effectively. But Germany had neither the fuel nor the time to provide that training. Many pilots died in their first jet flights, victims of poor training rather than enemy action. Approximately 1,400 Me-262s were produced. Only about 200 ever flew combat missions. Of those, Approximately 100 were lost to all causes. The jet fighter killed perhaps 150 to 200 Allied aircraft, a respectable tally, but utterly insufficient to affect the war's outcome. Albert Speer later calculated that if the Me-262 had entered production as a fighter in early 1944 instead of late 1944, and if Germany had concentrated resources on it rather than dispersing them among multiple wonder weapon programs, several thousand jets might have been operational by D-Day. Would this have changed the war? Speer thought probably not, but it might have made the final year far bloodier for Allied air forces. The Me-262's greatest contribution wasn't military, it was technological. After the war, both the United States and Soviet Union studied captured jets intensively. The swept-wing design influenced everything from the F-86 Sabre to the MiG-15. The Jumo 04 engine was reverse-engineered and improved. The tactical lessons learned helped develop jet combat doctrine. But in World War II, the Me-262 was too late, too few, and too misused to matter. Hitler's bomber obsession, material shortages, Allied bombing, fuel scarcity, training deficiencies, and strategic desperation combined to negate its revolutionary potential. It remained a what-if weapon, a glimpse of the future that arrived when the war was already lost. The Panzer VIII Maus, when bigger isn't better. In June 1942, Adolf Hitler summoned Ferdinand Porsche to his headquarters and asked him to design the largest, most heavily armored tank ever conceived. Hitler's instructions were specific. The tank must be impervious to any Allied weapon, mounting the most powerful gun possible, with armor thick enough to stop anything. Porsche, always eager to please Hitler and secure contracts, promised to deliver. What emerged was the Panzer VIII Maus, a name so ironically inappropriate for a 188-ton behemoth that it's almost funny. To understand how absurd the Maus was, compare it to other tanks. The standard German Panzer IV weighed 25 tons. The excellent Panther weighed 45 tons. The feared Tiger I weighed 57 tons. The Maus weighed 188 tons, nearly twice the weight of any other operational tank in history. The Maus measured 33 feet long, 12 feet wide, and 12 feet high. Its armor was 240 millimeter thick on the front, 200 millimeter on the sides, and 105 millimeters on top. This was armor measured in fractions of a foot. A Soviet 122 millimeter armor-piercing shell, which could penetrate nearly every other German tank, would bounce off the Maus at any range. The main armament was a 128 millimeter gun, the most powerful tank gun deployed in World War II. The secondary armament was a 75 millimeter gun, mounted coaxially. The Maus could theoretically destroy any Allied tank at ranges exceeding 2 miles, while being effectively immune to return fire. On paper, it was invincible. In reality, it was a 188-ton monument to engineering hubris. Only 2 prototypes were ever completed. The first one, V1, was finished in December 1943. Initial testing revealed problems immediately. The Daimler-Benz MB509 engine produced 1,200 horsepower, which sounds impressive until you realize it had to move 188 tons. The power-to-weight ratio was 6.4 horsepower per ton, compared to 15.6 for the Panther. Maximum speed was 8 mph on roads, about half the speed of a walking soldier. Cross-country speed was 5 mph. The transmission, trying to manage the enormous torque required to move this mass, overheated constantly. The engine consumed fuel at a rate that gave the Maus a range of approximately 120 miles on roads and less cross-country. But the real problems were logistical and tactical. The Maus was too heavy for any bridge in Europe. Germany's own military bridges were rated for 60 tons maximum. At 188 tons, the Maus couldn't cross rivers using bridges. It would have to ford them underwater, using a snorkel system for the engine. Yes, the Maus was designed to drive underwater across river bottoms. The hull was sealed, and a snorkel provided air to the engine. Testing at Kummersdorf proved this was technically possible, but operationally insane. The underwater crossing required calm water, firm river bottom, careful preparation, and luck. Any mechanical failure meant the crew drowning in a sealed metal coffin. Railway transport was equally problematic. The Maus exceeded the weight limit of German railway flat cars. Special reinforced cars had to be designed. Even then, the Maus's width exceeded railway clearance on many lines. It couldn't fit through tunnels. It couldn't negotiate sharp curves without derailing. If you needed to move a Maus from factory to front line, you'd have to partially disassemble it, load it onto special railway cars, ship it carefully on specific rail lines that could handle the weight, then reassemble it near the front. This process took days and required specialized equipment and personnel. Strategic mobility was non-existent. Tactical mobility was pathetic. The Maus couldn't keep up with infantry, let alone other tanks. Any advance would be limited to the Maus's 5 mph crawl. A Panther division could cover 80 miles in a day under good conditions. A Maus division could barely cover 25 miles, and that's assuming nothing broke, which was optimistic given the mechanical stress. Then there was the question of what enemies the Maus would actually face. By 1943 to 44, Germany was fighting a defensive war. The tactical situation required mobile reserves that could rapidly counterattack Allied breakthroughs. The Maus was the opposite of mobile. By the time it arrived at a breakthrough point, the battle would be over. The ammunition load was another problem. The 128mm gun could destroy anything, but it carried only 68 rounds. The 75mm had 200 rounds. In extended combat, the Maus would run out of ammunition quickly. Resupplying required specialized vehicles and equipment because standard ammunition trucks couldn't reach it in many tactical situations. The crew of 6 required extensive specialized training. The driver needed to understand the unique handling characteristics. The gunner had to master the complex fire control system. The commander had to coordinate the activities of an unusually large crew in an enormous vehicle. Training time was extensive, and trained crews were exactly what Germany didn't have by 1944. Cost was astronomical. Each Maus cost approximately 800,000 Reichsmarks, equivalent to 10 Panzer IVs or 4 Panthers. For the price of one Maus, Germany could have produced 4 excellent Panthers that could actually move, cross bridges, and fight effectively. Hitler, predictably, loved the Maus. He ordered production of 150 units. The Wehrmacht, looking at the specifications with horror, quietly tried to kill the program through bureaucratic obstruction. Field commanders who saw test footage were unanimous. This weapon was useless. General Heinz Guderian, Inspector General of Armored Troops and one of the architects of Blitzkrieg doctrine, stated in a meeting, "The Maus is a technical curiosity with no military value. It cannot be transported, cannot be deployed effectively, and represents a waste of resources we cannot afford." Hitler overruled him. Production continued, though at a glacial pace that reflected both manufacturing challenges and deliberate foot-dragging by industrial managers who understood the tank's uselessness. By January 1945, only 2 prototypes existed. V1 had the complete turret, but was used primarily for mobility testing. V2 had the complete weapons system, but incomplete armor. As Soviet forces approached the testing ground at Kummersdorf, German engineers faced a decision: try to use the Maus in combat or destroy it. They chose destruction. On April 14, 1945, German engineers set demolition charges and destroyed both prototypes rather than let them fall into Soviet hands intact. The Soviets captured the remains and, with typical Russian practicality, combined parts from both prototypes to create one functional Maus. It was shipped to Kubinka, where it remains on display today, a testament to engineering ambition divorced from tactical reality. The Maus represented everything wrong with German wonder weapon development. It was technically impressive, but operationally useless. It consumed resources desperately needed elsewhere. It reflected Hitler's obsession with size and power rather than practical military requirements. It diverted engineering talent from weapons that might have actually helped. The same resources that produced two Maus prototypes could have produced 20 Panthers or 80 Stu-Ge-3 assault guns, either of which would have been far more useful. The engineering hours could have improved existing designs or solved problems like the Panther's transmission failures. Instead, Germany produced a 188-ton curiosity that never fired a shot in anger, never influenced any battle, and never justified a fraction of the resources invested in it. The acoustic torpedo, technology without reliability. In 1943, German U-boats were dying in alarming numbers. Allied convoy escorts had become devastatingly effective at detecting and destroying submarines. The Type 7 U-boat, which had terrorized the Atlantic in 1940-42, was now a death trap. German scientists developed an innovative solution, the T5 Zaunkönig, Wren, acoustic torpedo. Instead of requiring precise aim, the T5 would home on the noise of a ship's propellers, turning even mediocre torpedo crews into deadly threats. The concept was sound. Microphones in the torpedo's nose detected propeller noise. The guidance system steered toward the loudest sound. Against slow-moving merchant ships, it should have been devastating. Initial tests were promising. The T5 reliably homed on target ships under controlled conditions. It could track propeller noise at ranges exceeding 1,000 yards. The warhead was powerful enough to break a destroyer's back. U-boat crews received the T5 in September 1943 with great excitement. Finally, a weapon that could strike back effectively against the escorts that were destroying them. The first combat use came on September 20, 1943, when U-645 fired acoustic torpedoes at convoy ONS-18. The results seemed impressive initially. German submariners reported hearing explosions, feeling impacts, seeing ships slow or sink. Kriegsmarine headquarters received enthusiastic reports of kills. But Allied records told a different story. Many reported sinkings never happened. Ships reported sunk by acoustic torpedoes arrived at destination ports intact. The kill claims were wildly exaggerated. What was happening? The T5 had fatal flaws that only revealed themselves in combat conditions. First, the acoustic homing was indiscriminate. The torpedo homed on the loudest propeller noise, which wasn't necessarily the intended target. In convoy situations with multiple ships, the T5 often homed on the wrong vessel or even on the U-boat that fired it. Several U-boats were destroyed by their own acoustic torpedoes. Second, the torpedo was vulnerable to simple countermeasures. The Allies quickly developed the Foxer, a noise-making device towed behind escorts. The Foxer created propeller-like sounds louder than actual propellers. Acoustic torpedoes homed on Foxers instead of ships, detonating harmlessly at the end of tow cables. Third, the T5 couldn't distinguish between targets. It might home on a worthless trawler instead of a valuable escort. It might chase one ship, lose tracking, then chase another, wasting fuel aimlessly. Fourth, the guidance system was unreliable. The microphones could be fooled by wave noise, cavitation, or the torpedo's own engine sounds. The torpedo might go straight, circle aimlessly, or even turn back toward its launch point. Captain Lieutenant Peter Kramer, commanding U-333, described firing a T-5 at an escort in October 1943. "I heard the torpedo running true, then it curved. I heard its propeller getting louder. It was coming back at us. I ordered emergency dive. We went deep. The torpedo passed overhead, missing by meters. That weapon nearly killed us instead of the enemy." The temperature sensitivity was another critical flaw. The acoustic sensors worked differently in cold water versus warm water. The Atlantic's temperature variations meant torpedoes calibrated in one area might malfunction in another. What worked near Norway failed near Gibraltar. Production quality was inconsistent. Each T5 required precision manufacturing of acoustic sensors, guidance circuitry, and complex mechanical linkages. Under wartime conditions, with bombing disrupting factories and skilled workers being conscripted, quality control was impossible. Some torpedoes worked perfectly. Others were defective from the factory. The most damning problem was that even when everything worked correctly, the T5 was only marginally more effective than conventional torpedoes. Analysis of combat records showed the T-5's actual success rate was approximately 5 to 7%, compared to 3 to 4% for conventional torpedoes. This was an improvement but hardly revolutionary. The cost was substantially higher than conventional torpedoes. Each T-5 cost approximately 50% more to produce while requiring scarce electronic components. For a marginal improvement in effectiveness, Germany was spending resources that could have produced more submarines or improved existing ones. By mid-1944, Allied countermeasures had made the T-5 effectively obsolete. The Fokker and its improved successors became standard equipment on escorts. U-boat commanders reverted to conventional torpedoes for most attacks, using acoustic torpedoes only in specific situations where they might have advantages. The T-5 program represented a recurring theme in German wonder weapons: brilliant concept, inadequate execution, and countermeasures that negated initial advantages. Like so many Nazi technological innovations, it arrived too late, worked imperfectly, and failed to change the war's trajectory. The Amerika Bomber, dreams of striking New York. In 1942, Hitler became obsessed with a new idea: bombing the United States, not just striking military targets, but hitting New York, Washington, and other cities to demoralize Americans and force them to divert resources to homeland defense. The technical challenge was extraordinary. No existing aircraft could reach the United States from Europe and return. The distance from Germany to New York is approximately 3,900 miles. This required an aircraft with nearly 8,000 miles range, carrying a meaningful bomb load at speeds high enough to avoid interception. The Luftwaffe issued specifications for the Amerika Bomber in 1942. Multiple companies submitted designs, each more ambitious than the last. What emerged were some of the most bizarre aircraft concepts in aviation history. The Messerschmitt Me 264 was the most conventional design. It looked like a scaled-up bomber with 4 engines, huge wings, and fuel tanks occupying most of the fuselage. 3 prototypes were built, and testing revealed fundamental problems immediately. Range with a bomb load was approximately 6,000 miles, sufficient to reach the U.S. but not return. This meant crews would have to bail out over the Atlantic, ditch near neutral countries, or attempt one-way suicide missions. None of these options appealed to Luftwaffe planners. Speed was another problem. The Me 264 could manage about 340 mph, painfully slow by 1943 standards. American P-47 and P-51 fighters could intercept it easily. Without fighter escort over the Atlantic, the bomber would be defenseless against any defending fighters. The bomb load was pathetic relative to the aircraft's size. The Me 264 could carry approximately 4,400 pounds of bombs to New York. By comparison, a standard B-17 carried 4,500 pounds on missions over Germany, while being much smaller and requiring far less fuel. What strategic effect would dropping 4,400 pounds of bombs on New York accomplish? The answer was obvious. Essentially, nothing. One aircraft dropping a few thousand pounds of explosives on a city of 8 million people would cause minimal damage and zero strategic impact. The Horten Ho 68 was even more ambitious. The Horten brothers, specialists in flying wing designs, proposed a massive jet-powered flying wing that would use boundary layer control to achieve unprecedented efficiency. On paper, it could reach America and return. In reality, the Ho 68 existed only as wind tunnel models and drawings. The technology required didn't exist. Jet engines capable of providing sufficient thrust at acceptable fuel consumption weren't available. The materials needed for such a large flying wing weren't producible. The control systems were theoretical. The Junkers Ju 390 got furthest in development. This was a 6-engine monster created by extending the Ju 290 Maritime Patrol aircraft. 2 prototypes were built, and one allegedly flew within 12 miles of New York in August 1944 on a reconnaissance mission. This claim is controversial and disputed by many historians. Luftwaffe records don't definitively confirm the flight. American radar and fighter patrols logged no unidentified aircraft. The story may be myth, exaggeration, or genuine event that was successfully concealed. What's undisputed is that even if the Ju-390 could reach America, it couldn't do so carrying meaningful bomb loads. The 6 engines consumed fuel voraciously. The aircraft needed nearly every available pound of capacity for fuel, leaving minimal weight for bombs. The strategic logic of the Amerika Bomber was fundamentally flawed. Even if Germany developed an aircraft capable of striking New York, what would this accomplish? Bombing American cities wouldn't stop American war production, which was dispersed across the continent. It wouldn't force surrender from a nation that had already committed to total victory. It would likely harden American resolve and justify even more aggressive warfare against Germany. The resources required to develop and build Amerika bombers were astronomical. Each aircraft would consume materials equivalent to dozens of fighters. The specialized engines, fuel systems, and components required would divert industrial capacity from weapons actually needed. Germany in 1943-44 desperately needed fighters to defend against Allied bombing. Every day, hundreds of B-17s and B-24s struck German industrial facilities. The Amerika Bomber program consumed resources that could have produced defensive fighters. Albert Speer, viewing the Amerika Bomber proposals, reportedly said, "Building aircraft to bomb America is insanity when we cannot stop America from bombing us." By late 1944, the program was effectively dead. The prototypes that existed were either destroyed in Allied bombing raids or scuttled as Allied forces advanced. The dream of striking New York died with the Reich. The Amerika Bomber represented Hitler's fundamental misunderstanding of strategic bombing. He believed that bombing civilians would break morale and force surrender. This was the same logic behind the V-weapons, and it was equally wrong. The British had endured the Blitz without surrendering. The Germans endured Allied strategic bombing without surrendering. The Japanese endured firebombing of their cities without surrendering. Civilian bombing, while horrific, rarely achieved strategic objectives against determined nations. What broke nations was the destruction of military forces, the loss of territory, the collapse of industrial capacity, and the exhaustion of resources. The Amerika Bomber would have accomplished none of these things. If you found this history fascinating, let us know in the comments what other World War II weapons programs you'd like us to explore. Subscribe to see more deep dives into military history, where we examine not just what happened, but why it happened, and what we can learn from it.